can estimate to be 10 years, 20 years, it's very hard to tell. But what I think is very important is that the research continues because it can be potentially transformative for our computational field. On the way to develop the quantum computers, we are already finding new breakthrough technologies, and then we can also find a lot of technological spillover. So I am Fabio Donati, I am Italian. I'm group leader here at the Center for Quantum Nanoscience and Associate Professor of Physics at Iowa Women's University. So I earned my degree and PhD in Italy, in Politecnico di Milano, and then I had a brief experience at the Max Planck Institute in Halle, in Germany, before I started working as a researcher in Switzerland at the École Polytechnique Fédérale de Lausanne, where I worked for 6 years before joining Korea. So now it's been nearly 8 years I've been living and working in Korea. Definitely, there are different approaches to develop a quantum computer nowadays. We can distinguish them in two main categories. The first one includes the solid-state platforms, for example, like the superconducting qubits, the one that are used by IBM and Google, or silicon quantum dots used by Intel, and also diamond-based systems, such as the one that many companies, mostly startups, are using, like Quantum Brilliance. These platforms have a big advantage as they can be fabricated in the form of chip. So this makes them easier to integrate with classical computer. While this technology have faced traditional challenges with the qubit quality, recent advances has also made it possible to close the gap in this sense. But there is a second group which instead uses either neutral atoms or trapped ion that actually they are suspended in a vacuum using and controlled using lasers and electromagnetic fields. So these qubits, they have a very high quality, and normally their fidelity is very high. Normally they operate a bit slower and they are a bit more complex to integrate in a single chip. So both platforms have advantages and disadvantages. There are also emerging approaches that maybe at the moment they are not really competing to the race of the most performant computer right now, but they could be very significant on the long term. For example, Microsoft is heavily investing in topological qubit, which, although they are still in their early stages, they could be really important to deliver exceptional fault tolerance in the future. So if they can make the technology practical, it could really be a game changer. And then also let me mention that here at the Center for Quantum Nanoscience, we are also working on an independent platform which is based on magnetic atoms on surfaces. This approach is also in early stages, and there are challenges about the quality of the qubit and also scalability. However, there is a very big advantage with this platform, which is the miniaturization. So we can create a quantum gate using just a few atoms. So this is the smallest portion of material we can use to make a device. With this framework, my research focuses on identifying novel atomic scale quantum materials based on some sort of elements that are called rare earths, and also to develop fundamental approaches that could be one day used to tackle challenges of the extreme miniaturization in quantum computing. So I think the benefit of having all this platform is that the advantage that has been found in one can be used to push the other technology forward. So in a way, I expect a lot of technological spillover in developing this technology in parallel. And I think this altogether can build up a sort of a collective momentum that can help our community to build high-performance quantum computers. So Google's new quantum computer called Willow is actually a big step forward, I think, in two main areas. One is the quality of the qubit, which are the main building blocks for a quantum computer, and its error correction capabilities. So these improvements actually make calculation much more reliable, and this is a crucial point for researchers to explore the next generation of quantum algorithms. So this means that quantum computers are becoming more and more attractive as an option to solve problems that we used to be able to handle only with classical computers so far. So what's interesting is that also IBM did something similar with their Heron quantum computer that they released nearly 1 year ago. So this is a clear sign that big players like Google and IBM are shifting their focus. So instead of just racing to cram in more qubits in the same system, they are now making a focus on making the quantum computer more useful and reliable to solve real-world problems. I think this is an indication that the field is becoming more mature. So related to this question, I have to say that I think that these innovations will really benefit researchers that are tackling more and more complex problems these days. So I'm sure that researchers will be able to demonstrate that for some problem, quantum computer can perform better than classical computer. And I think this is very exciting and could lead to transformative discoveries. That said, I think we still need to consider quantum computers as a sort of experimental tools, rather than devices that will immediately change our everyday life or the way businesses operate. I think for this kind of transformation, we need to wait a little bit longer, maybe a few years at least. So this is my expectation. So we cannot tell now when, let's say, the main development of quantum computer will take this to a step where we can really say, oh, this is a tool that is useful for everyday life. We can estimate to be 10 years, 20 years, it's very hard to tell. In my opinion, it's very important to appreciate every step we take in this journey, because at this moment in time, we can only solve a few problems, but we have in our community many high-impact papers published in international journals that demonstrate how powerful it is to work with a quantum computer to solve a research problem these days. And this is just the beginning. So I think rather than just asking ourselves when will it be on the market, but rather than what can we do with the next step? So how many more problems we can solve? That will open up more and more the possibility to appreciate what quantum computing community is doing for the society. And I think we all look for something new in our science and technology. So quantum computing, of course, is attracting a lot of attention in this sense, which is good and bad, in the sense that good because it pushes forward with more energy of the whole field, but bad because maybe we also create questions about, is it worth investing so much in quantum computing right now? And again, if we just focus on the final product, we may not know the answer now, but if instead we keep looking at the journey that we are making and on the environment we are creating, I think there's no doubt that it's worth keep going in this direction. Yeah, this is a very important question. As we discussed during the forum, today's quantum computers are in what we call the noisy intermediate scale quantum era. In this stage, essentially, a quantum computer can be better than classical computer in some specific problem, but they are not powerful enough to solve most of the real-world problems. But what I think is very important is that the research continues because it can be potentially transformative for our computational field. So I think every step we take forward, either in the hardware or software or error corrections, actually it brings us closer and closer to the application. And I also want to bring the attention on the fact that not only the final product is important, but the journey matters a lot. Because on the way to develop the quantum computers, we are already finding new breakthrough technologies, and then we can also find a lot of technological spillover. So already by investing our energy and effort in this sense, it's already producing results that are beyond our expectations. And not only in the quantum computing field, but in cryptography, optimization, material science. So there are already benefits in just working on this field, not even for the final product. Well, I think we have to be fair in comparison. If I think about when diode and transistor were developed back then, so the mindset of the people were also not very much ready with this kind of logic. Even binary algorithm with 0 and 1 were already quite difficult to grasp from the general public back then. So we should maybe get back maybe to the 60s or the 70s when the first computer were invented and developed, and see how people were reacting in front of these new devices. Then, of course, in our mindset now, it's about maybe 50 years we are used to this development of computer and semiconducting technology. So we are more and more used to this kind of development, and we sort of understand more about that. But now we are in front of a change of paradigm. So quantum computer use completely different concepts, and definitely the devices also operate on the principle of quantum physics, which are generally very difficult to picture in our mind because we live in a classical world, and normally quantum phenomena are just at the atomic scale, electron scale or so. But I must say, our new generation of students, they are trained on quantum physics and quantum mechanics, so I expect that many more of them will be ready with their mind to understand what happens. Of course, the role of the researcher and professor and scientist in general is to make this topic more and more understandable to the general public. And I think in the last maybe 5 or 10 years, there has been a lot of effort in making this happen, but definitely until the moment we cannot provide a clear example of what a quantum computer can do in real life problem solving, then of course it's going to be a little bit more like a science fiction example. So I think we have to be a little bit more patient and see on one side the generation of the researcher student growing in their mindset. On the other hand, when we have a significant application, then it will be much easier for us to explain to the general public what is the quantum computer useful for and how it operates. So globally, the investment in quantum computing are estimated to about $42 billion all over the world. So the leading countries in this field are US, China, and European Union, which have all launched multi-billion-dollar initiatives. There are, the major investment is from government at this point, but there are also significant investment from private sector, especially from the major IT corporate like IBM, Google, and Microsoft. But we see also a growing number of startups in the field. This investment is not only important to make the final product, as I mentioned, but also we are building a whole ecosystem about quantum computing. So this is actually the main purpose of many government funding, which is to foster international collaboration, training skilled workforces, and supporting also fundamental research. So it's important not only to look at the final development of the computer, but also what we are creating around it in terms of society. And I think if we work together in this sense, I think quantum computing can become a reality. Yeah, that's a very critical point. So this also boils down to the fact that there are different dynamics between development of researches and investment cycles. I would say government and cycles normally go with the period of election time, so you normally invest on a time of a few years, and company even shorter term. So what we can see, for example, from the oscillations of the investment is that for the government, the investment has been more steady growing, but for companies it has been fluctuating more depending on also how much they get support from governments. So this also tells us that this time frame can be mismatched with the fundamental discovery about quantum computers, because years is a typical timescale of development technologies. So if the technology has already reached maturity, then you can improve it on that timescale. But we are still looking for fundamental breakthrough to make really the quantum computer through, let's say, the final product to the market. So if we think that from the fundamental discovery, we have to create a technology, make it mature, and then having a final product, this cycle is normally longer. It can take maybe 10 or 20 years. So what can happen is that now we have a lot of excitement about quantum, we invest a lot, and this investment is not lost. We are learning a lot. But it's true that maybe in this cycle of investment, we will have a breakthrough discovery at the fundamental level. And probably it's okay even if we have to face something that people are afraid of, like a quantum winter in terms of investment. That's okay, because the money is not lost. We have learned things, and then through the winter, we will push through the discoveries and make new technologies. And I think we can just need to wait for, if this winter happens, we need to just wait for the next cycle, because as the fundamental discovery will become technology, then the fact that they become mature will be a cycle that probably start with the next one for the investment. So to come back to your initial point, yes, it could be that now we are a bit overheated, and so we will cool down soon. But these cycles are natural, and as long as we keep studying and pushing our discoveries to the line of our planning of the development, I think it will continue and survive different cycles. So, as I mentioned in the beginning, our center is part of the Institute for Basic Science. So we are really focusing on fundamental research. This makes us not so attractive for maybe companies at this point in time, because what we study now is not directly becoming a technology. But as I mentioned, it's important to make sure that there is a chain between the fundamental research until the final technology. So we are taking the first part. So in this sense, our research is mostly funded by the government, and we hope that what we discover will become a technology later. So for us, rather than looking for investment from company, we try to have a cooperation with other research institutes in the world, like in Europe, in many countries like Switzerland or US, to make sure that we have a network of specialists. We can also send our students to do collaborative research abroad and learn from other centers, and also share knowledge with them. So this contribution is mostly to foster the network and the environment, so let's say the ecosystem of the quantum. Let me say how I feel, because I've seen quantum computing developing while I already was doing research in the field. And I think the difficult part is to change our mindset about this quantum computing. The main reason is quantum computing works with a completely different logic. So quantum algorithms, they are differently thought with respect to the classical ones. And so we cannot just rely on one specific field to develop our mindset. We need to be open. And for a student, I would say, do not get scared. It's difficult. It's very much mind-blowing to understand all these new concepts. So you have to incorporate some concepts from physics, engineering, IT. And of course, the difficult part is to take what we need from all these fields and condense it into organic knowledge that we can deliver to students. So my suggestion is be brave, try to get into the field, and definitely, even if you feel it's difficult, you will learn a lot. And what is the reward is that the mindset will be completely different and will be helping a lot solving future challenges.